Hi, in this video I am going to solve the problems related to lecture 9, the first part of factorizing polynomials. It relates to week 13. Yes? Okay, part A is given as follows. Factorize the following polynomials. Okay, so I will factorize them one by one here for you. Okay, so I have this expression given 7x to the 3 and then y3 z minus 21x squared y to the 3 z to the 3 minus 35x to the 4 y squared and then z6. We want to factorize this. Okay, it's very simple. You see that 7, 21, and 35. 7 is the common factor between x to the 3, x to the 2, and x to the 4. X to the 2 is the common factor, and exactly for the other variables. So what can I take out is a 7 from numbers, x to the power of 2, and then from y, I have also y to the power of 2, and from z, I have only z. So I have to divide these one by one to this, and I will write the answer. So 7x squared y squared. So what is left for me is 1x left here, and 1y is left. No z is left. Yes. And then here I will have minus 3, and then I have 1y and z to the power of 2 left. And then here I will have 5, and then I have x to the 2 and z to the power of 5. Yes. So you can just multiply this back to check that everything is right. If you multiply this here, it becomes exactly that expression. Multiply it here, x squared y to the 3 z to the 3, that's right. And if I multiply this there, it becomes minus 35 x to the 4 y to the 2 and z to the 6. It's completely right. Okay. So now let me go to number 2. So number 2 is 2x to the 5, and then I have 4x to the 3 plus 2x. Okay? So you immediately see that 2x is a common factor, so you can pull it out. So 2x, what is left from here is x to the 4, and then here I have 2x to the 2, and then I have 1. Yes? Of course, you see that this is already in the factorized form, but you know that you need to continue as much as possible. And then hopefully you can realize that this is the quadratic pattern, so you can even continue and write it as x to the 2 plus 1 to the 2. Yes, the first one to the 2, 2 times the first one times the second one, and the second one to the 2. Okay, number 3. So number 3, I am supposed to factorize this expression, x to the 4, y to the 2, and z, plus 16z minus 8x squared y z. Okay? So again, I told you that the priority is always given with this method. If you can pull out something from all the terms, that has the priority over other methods that we will learn in the future. Okay? So here I can see that z is a common factor. So before continuing anymore, I factor z out. Then here it becomes x to the 4, y to the 2, and this becomes 16. And then this becomes minus 8x squared y. Okay? But then you see that I have a trinomial, and 2 of them are complete squares. So you get suspicious that it might be the quadratic pattern. But how can you make sure? You go to a scratch paper, for example, you take the square root of this, it becomes x to the 2y. You take the square root of the other one, which becomes 4, you multiply them, and you yourself multiply by an extra 2. Then what will happen here is 8x squared y, and that is exactly this term. So it is indeed a quadratic pattern. So what can I do? I can copy paste this z, and then I have this to the power of 2. I would take the square root of this, it will give me x to the 2y. Take the square root of this one, gives me 4, but because this is negative, I put negative in front. And I cannot continue more, so that's the end of the factorization of this polynomial. Okay, so let me go to number 4. So number 4 is x minus 2y to the 2, and then you have minus 10 and x minus 2y plus 25. Yes? Even though this expression is not a trinomial, but it is written in the form of trinomial, a polynomial with 3 terms. But you need to consider this whole thing as the first term, and this whole thing as the second, and this one as the third. And then if you interpret it in this way, you immediately realize that you have 2 complete squares, yes? One of them is this complete square, and the other one is 25. So again, you might think it might be the case that this is going to be a quadratic pattern. So how should I make sure? If you want, you can go to a scratch paper, or it's not that hard. Let us do it in our head. Yes, x minus 2y, you take the square root of that, it becomes x minus 2y. You take the square root of that, it becomes 5. You multiply them, it becomes 5 times x minus 2y, and then you multiply by an extra 2, it will give me exactly this. So that is indeed a quadratic pattern. Okay, so what I do, I write something like this, yes, and then I would say I put the square root of this here, and then I put the square root of this one here, and because this sign is negative, I put negative, yes. But nobody needs these pair of brackets anymore, so I remove them simply. Then it becomes x minus 2y minus 5 to the 2. And that's the final answer to this problem. Okay, so number 5. So number 5 is 2x to the 4 minus 1 to the 2 plus 2 times 2x4 minus 1. And then I have 1 minus 2y4. And then I have plus 1 minus 2y to the 4 to the 2. Okay, but immediately you can realize the pattern, even though this is not a trinomial technically, but it is written in the form of a trinomial. And then in this trinomial, you see that you have 2 complete squares. So it means that it might be the case that this is the quadratic pattern, and indeed it is. Yes, why? Because if you take the square root of this, it will give you this. And if you take the square root of this, it will give you this. If you multiply them, you will get this one, and we always multiply by an extra 2. So that's exactly the quadratic pattern. So what you do is to write this. Take the square root of that, and then take the square root of the other one, and then because this is positive, you put positive in between. But I told you that when you reach to this point, because you can simplify this factor in its own right, you have to simplify that. It might be the case that you still can continue and make your factorization complete. And this is indeed the case here, because I can safely remove these brackets because they are positive, and then you see that this minus sign and this sign will cancel. And what is left for me is 2x to the 4 minus 2y to the 4, and then to the 2. So it's even though it's in the factorized form, but it's not fully factorized, I have to factor 2 out. So then it becomes 2x4 minus y4 to the 2. But because this is a product to the power of 2, this becomes the first one to the power of 2 and the second one to the power of 2. Yes, but hopefully you realize that this is still not complete because that's a conjugate pattern. So I can factorize this. It becomes x to the 2 minus y to the 2, x to the 2, y to the 2, and then the total expression to the 2. So instead of x to the 4 minus y to the 4, I just wrote this expression, and then I have a power of 2. But still, it's not complete, yes? X squared minus y squared forms another conjugate pattern. So if I continue, it becomes 4. I can write x minus y, x plus y, and x squared plus y squared. And I already told you that usually the sum of the squares if you want to continue, you have to use complex numbers, which is probably not by the it's not our intention. Okay, of course you can write it in that way, but instead of putting that power 2 there, it's better to write it in this form. Yes, so that is the factorization of this expression. Yes, now number 6. So number 6, I'm supposed to factorize this expression. X squared plus y squared to the 2 minus 4x squared y squared. Okay. Here, of course, you can have 2 different methods to calculate that. Yes. So you might think that I raise it to power 2, simplify this, and then try to see what happens. That's also that's correct. So let me just do it here. I raise it to power 2. It becomes the first one to the 2. 2 times the first one times the second one, and the second one to the 2. And then I have minus 4x squared y squared. Then you can see that I can write it, this one and this one are simplified, and I will get minus 2x squared y squared plus y4. And then it becomes x squared minus y squared to the 2, because that is now a quadratic pattern. So, but this is a conjugate pattern, so it becomes x minus y, x plus y, totally to power 2, but that's a product, so I can write it in that way. So that is one way that's completely valid. But here, my intention was not using this method. I wanted you to see the conjugate pattern from the beginning. Of course, that's completely valid. So this is one way. So method 1. So method 2. So I prefer this one here. Okay, I will talk about these kind of methods later in more advanced factorizations. But here, let us just do it as we did for the conjugate pattern. So here, I would write it as x squared plus y squared to the power of 2. Instead of this expression, I write 2xy to the 2. Then I can see the difference of 2 squares. Then immediately I realize that I can use the conjugate pattern. So what happens, it becomes the first one, the square root of the first one, minus the square root of the second one, multiplied by the square root of the first one, plus the square root of the second one. Then hopefully you can realize that this one is the quadratic rule. It's x minus 1 to the y to the 2, and the other one is x plus y to the 2. Yes? That's okay. Okay, now let me go to number 7. So number 7, I have a to the 6 minus b to the 6. Okay. First, I see that I have the difference of 2 complete squares, so I can use the conjugate rule, yes? So it becomes, so I can write it, so let me write it in this form. a6 minus b6 can be interpreted as a to the power of 3 to the 2 minus b to the power of 3 to the 2. Yes, so these are 2 complete squares, and I have the difference of 2 complete squares. So this gives me the conjugate pattern. So a3 minus b3, then I will have a3 plus b3. But hopefully you remember that these are also famous identities, the difference of cubes, the sum of cubes. So what can I write? The factorization of the first one can be written in this form, and the factorization of the second one can be written in this form. Yes? So one thing that I want to mention here is that you might think, and that's correct, of course, you might think, why I cannot write this. You can interpret a6 as a to the 2 to the power of 3, and then b to the 2 to the power of 3. And that's also correct. Yes? A to the 2 to the 3 is a6. A to the 3 to the 2 is also a6. So we were able to solve the problem in that way, and that's fully factorized in this form. But if I interpret it in that way, then it becomes the difference of cubes. So I can use that identity that I used here, the difference of cubes, but instead of a, I have a squared, instead of b, I have b squared. But no problem, it becomes a squared minus b squared. Then the first one to the 2, the product of these two numbers by the opposite sign, and then this one to the 2. The first one to the 2 is a4, and then this is also b4. But then you can realize that this can be factorized in this form by conjugate pattern, but this one will be left. And then you might think that there is some discrepancies here, because here a minus b, a plus b, but instead of having these two factors, I have this one. I will teach you later how we can factorize this in these two expressions, yes? So it's not hard for yourself. You can work it at home. You multiply this by that. That's the conjugate pattern. This becomes a squared plus b squared to the 2 minus ab to the 2. If you calculate that and expand it, it becomes exactly this. But how to go from here to here is the topic of another method of factorization. We have to add a term and subtract a term. Sometimes we can add and subtract, okay, and then sometimes the new pattern, and a pattern will actually emerge. So here, if I add a squared b squared, so it becomes a to the 4 plus 2a squared b squared plus b to the 4 minus a squared b squared. Okay, I will talk about this later. But for the time being, if I ask you to factorize that, if you factorize it in this form, it's not complete, yes? Because this can also be factorized more, even though we haven't studied that yet. Okay, so I will consider this the solution of this problem, even though this is also completely reasonable and correct. The reason that we stuck here and we cannot continue because it needs another method that will come later. Yes? Okay. So let me go to number 8. Number 8 is a to the 9 minus b to the 9. Okay, so here there is no matter of confusion. There is only one way to write this. This is a to the 3 minus b to the 3 to the 3. So, but this is the difference of two complete cubes. So then it becomes the first one minus the second one, but multiplied by the first one to the 2, the product of them with the opposite sign, and then the second one to the 2. But this one itself is also the difference of cubes, complete cubes. So I can write it again with the same formula. So a squared plus ab plus b squared, and then I have a to the 6 plus a to the 3, b to the 3, b to the 6. So that is the factorization of a to the 9 minus b to the 9. Okay? So let us go to number 9. Number 9. I have a 16 a to the 3 minus 54. Yes? Okay. What can I do here? You immediately realize that there is something in common between 16 and 54, and that is 2. Yes, so I can factor 2 out first. Then it becomes 8a to the 3, and this becomes 27. But hopefully you can immediately realize that this is the difference of two complete cubes. Why? Because the first one is nothing except 2a to the 3, and then the second one is 3 to the 3. And that is the difference of two complete cubes. So then you can use the formula. The cubic root of the first one minus the cubic root of the second one. And when you write when you want to write the longer brackets, you need to write it in accordance with the smaller one. The first one to the 2, the product of them with the opposite sign, so it becomes positive 6a, and this one to the 2, which is 9. Okay, you might, so yeah, that's the end of the problem. It seems that this is a quadratic pattern, but it is not. Why? Because if I take the square root of this, it's 2a, the square root of this is 3, and if you multiply it by an extra 2, it becomes 12a, not 6a. So that is the end of the problem. Okay, so number 10, I have a to the 6 plus 2a to the 3 plus 1. Hopefully you can immediately realize that this is a quadratic pattern. Why? Because I have a trinomial and 2 of them are complete squares. So I will get suspicious that it might be the case that it's a quadratic pattern, and indeed it is. Because if I take the square root of this, it becomes a to the 3. Square root of that, it becomes 1. If I multiply them, it becomes a3, and if I multiply by an extra 2, it becomes exactly 2a to the 3. So this becomes a to the 3 plus 1 to the 2. But if you stop here, that's not complete, because now we have the sum of 2 complete cubes. A to the 3 is a complete cube, and 1 can be written as 1 to the 3. That's also a complete cube. So then I have to factorize it using that identity, a plus 1, and then this becomes a squared, the product of them with the opposite sign, and then this one to the 2, and then totally to the 2. But it is better to write it in this way, a plus 1 to the 2, a squared minus a plus 1 to the 2. Yes? So I go to number 11. So let me write 11 here as well. So number 11, I am supposed to factorize 5 minus 5 2x minus 3 to the 2. Yes? So you can immediately realize 5 is in common, so I can pull it out. So it becomes 5. And then I will have 1 from here, minus 2x minus 3 from here to the 2. And then hopefully you can realize that this is the difference of 2 complete squares. This is evidently complete square, and 1 can also be written as 1 to the power of 2. They are the same thing. And then you can see the difference of 2 complete squares. So it is the conjugate pattern. So the square root of the first one minus the square root of the second one multiplied by the square root of the first one added with the square root of the second. But I told you that it is always necessary to continue and simplify the left factors. Yes? Okay, so let us do that. So if you multiply this minus inside, it becomes negative 2x, and then negative becomes positive 3, and positive 1 becomes positive 4. So if I want to continue here, it becomes 5. Then I will have positive 4 minus 2x from the first pair of brackets. And then here I have 2x, so I would write it 2x. And then if you see, I have 1 here and minus 3 there. Yes, it becomes minus 2. But this is not complete because I can factor a 2 out here. It becomes 2 minus x. Here I also can factor a 2 out. It becomes x minus 1. 2 times 2 times 5 is 20. And then I have 2 minus x and x minus 1. This is the factorized form of this expression. So let me just do number 12. So number 12 is this expression, 18 a to the 3 plus 4b to the 3, and then I have to the 2, minus, I have 9a to the 3 minus 5b to the 3 to the power of 2. Double check. Yes. So we want to factorize this. It's very clear that I have this difference of 2 complete squares. So I use the conjugate rule. So it becomes the square root of the first one, yes, minus the square root of the second one, multiplied by the square root of the first one plus the square root of the second one. Yes? This is the conjugate pattern for the time being. And I told you that we have to simplify each factor. So can we simplify it? We can do it in our head, yes? If I multiply this negative sign inside, it becomes negative 9a cubed, but I have a positive 18a cubed, so it becomes 9a cubed at the end. And I have 4b cubed minus minus becomes positive 5, positive 5, positive 4 becomes positive 9b cubed. Yes. For the next one, I have 18 and 9, it's 27. And then I have 4b cubed minus 5b cubed is minus b cubed. Yes. Okay, here I have a factor of 9 that I can pull out, so I have to do that. Then it is left with a cubed plus b cubed. Here I have the difference of two complete cubes, yes? First one I can write 3a to the 3 minus b to the 3. And both of them are factorizable more, yes? This is the sum of two complete cubes. This is the difference of two complete cubes. So we continue. So then it becomes 9. Then I have a plus b, a squared minus ab plus b squared for the first term, for the first factor. For the second factor, the cubic root of the first one minus the cubic root of the second one. Then the first one to the 2, the multiplication by the opposite sign, and finally b squared. So this expression is the full factorized form of this expression. So number 13. So let me try to find the number 13. Okay, yes, 13 is also a good one. So let me write it here for you. So it is number 13. It's 4b squared c squared minus a squared minus b squared minus c squared to the 2. Okay, so we want to calculate this. So I hope that you can see the difference of two complete squares immediately. Yes, how? Because this is a complete square if I write it in that way, and this is already written in the complete squared form. Yes, so I can use the conjugate rule. The square root of the first one minus the square root of the second one, and then the square root of the first one plus the square root of the second. Yes. So here I have to multiply this negative sign inside if I want to go further. Yes, because I have to make sure that I cannot go further if it is really not possible. So then it's 2bc, I multiply this negative sign inside, and then I can write it as this. Yes. Okay. But then hopefully you can immediately realize that this is a quadratic pattern. So I can write it as b plus c to the 2 minus a squared. Yes. Here, it's also a quadratic pattern, but with the wrong sign. And I told you that you already have this experience. If you have the wrong sign, you have to factor a negative sign out, yes? So here I can write a squared first, and I can write negative, and then I put positive b squared, negative 2bc, and positive c squared, yes? So let us recheck everything is right. A squared is a squared. Minus b squared is minus b squared. Minus minus is positive 2bc, and minus positive is negative c squared. But what is the benefit of that? The benefit is that the second one becomes a quadratic pattern again. And then again, I have the difference of complete squares here and there, so I have to use the conjugate pattern. So the conjugate pattern gives me the square root of the first one minus the square root of the second one, the square root of the first one plus the square root of the second one. Here, the square root of the first one minus the square root of the second one, the square root of the first one plus the square root of the second one. And then let us remove the brackets which are not necessary. So here I can safely remove it. And here I can also safely remove it. Here I can remove it, but I have to multiply the negative sign in, so it becomes negative b plus c. Here I can safely remove it, and I don't need to change anything. So that is my expression in full factorized form. Yes. And finally here in this problem number 14, let me also do number 14 for you. So number 14, we are supposed to factorize this expression. Yes. That is also the pattern of the difference of two complete squares, yes? So that's more or less very similar in a spirit to this problem. So I would write it as 2xw plus yz totally to power 2 to make it clear that this is a complete square. And then that one as well. That's also, yeah, we can just repeat this one. That's exactly, I'm just copy and paste the second. But now I have the difference of two complete squares, so it becomes the square root of the first one, yes, minus the square root of the second one, and then multiplied by the sum of these two, yes. Okay, now let us simplify each factor if possible. So I multiply this 2, and then I multiply this negative sign. Here I also multiply this, and then I remove these brackets. Yes? But then I think it's very easy for you to realize what you do. So you see this one and this one and this one makes a quadratic pattern. So it becomes y plus z to the 2. But again, this has the wrong sign. Yes. So if I take negative sign here, this becomes positive x squared, positive w squared, and then this becomes negative 2xw. So I can write it as x minus w to the 2. If you don't believe, let us recheck that one. I need to raise it to power 2, it becomes x squared, then I multiply it by a negative sign, it becomes negative squared, x squared. 2 times the first one times the second one is negative 2xy, xw. Then I multiply it by a negative sign, it becomes positive. And then the second one to the power of 2 becomes positive w2, but then I multiply it by an extra negative sign, it becomes negative w2. So everything is in order. Yes, I can do a similar thing there. So it becomes this one, and this one, and this one, and this one. I can write it as a complete square again. So it becomes w plus x plus w to the power of 2. Then again, for the same reason, I can, between these three, I can take a minus sign out first and then raise it to power 2. Y and z, sorry. This is y and z to the 2. Yes? So let us double check. The first one to the 2 multiplied by a negative sign. 2 times the first one times the second one. It becomes negative 2yz, but when I multiply it by a negative sign, it becomes with the positive sign. And then negative to the power of 2 becomes positive, but because of an extra negative sign, I will get negative at the end. But then you see that each one of them is actually the difference of 2 complete squares. So then I can use it. The square root of the first one, let me remove the brackets, minus the square root of the other one, which becomes negative x but positive w. And then I have the sum of them, and this one the same, yes? Negative of this means negative y, positive z, and then x plus w plus y minus. So that is the full factorized form of my expression, yes? I hope that you have gained a lot of skills and experience in factorizing these kind of polynomials. Then from this week, actually, I started to add some problems related to the previous lectures to help you not to forget what you learned before. So the only challenging problem that I actually wrote for you here for this set is something related from what we learned before, okay? Yeah, it's a little bit tricky, but I have given you a hint how to proceed. So hopefully by the experience that you gained so far from the previous lectures and then this hint, you will be able to solve the problem. So let me write the problem here for you. So this is part B. Yes, I have some numbers x1 till xn are set to be real numbers. And I know that we have this expression, x1 minus 1. I have this relation, x1 minus 1 square root plus 2 times x2 minus 4 square root plus 3 times x3 minus 9 square root. And then I continue until n square root of xn minus n squared. And on the right hand side, I have 1 over 2 x1 plus x2 plus x3 plus up to xn. Yes. So there is only one piece of information apparently provided for you here. I know that this is equal to that expression, and I am supposed to find all these unknowns from x1 to xn. Yes, and I have provided you the hint that turn this expression into the form of the sum of complete squares in complete squares. Okay, so what we can do now. So first of all, what I wanted to do is to get rid of this 1 over 2. So I multiplied both sides by a factor of 2. So then what will happen here? By the way, do you see the pattern? Why it is 1 and 4? It means that I have this number 1 here, then it becomes 2, then it becomes 3, and it continues until it becomes n. This is x1, x2, x3. It continues until it becomes xn. And this 1 is actually 1 to the 2. This is 2 to the 2. This is 3 to the 2. And it will continue until it becomes n to the 2. Yes, so that pattern becomes clear. Now, so what I do, I multiply both sides by a factor of 2 to get rid of this 2 there. So then it becomes 2 square root of x1 minus 1 plus 4 square root of x2 minus 4 plus 6 square root of x3 minus 9 plus we continue until this last one becomes 2n square root of xn to the xn minus n squared. On the right hand side, this 2 is gone, so I have x1 plus x2 plus x3 plus up to xn. Yes? Okay. So what I do next, I want to move all these terms. So let me check which one is better. Yes. So I will move all of them to the right. So then I would write it in this form. I would write x1. I move this one to the right and write it close to this one. So it becomes minus 2 square root of x1 minus 1. And if you don't mind, let me put brackets around. Okay, let us repeat. Plus, I have already x2 there. I move this term to the right, it becomes negative, and I write it next to x2, and then put them in brackets. The next one for this, I have already x3 there. I move this one to the right, it becomes negative, and I write them next to each other. And then finally, if I continue, I move this one to the left, it becomes xn minus 2n x squared, xn minus n squared. And then what is left? I moved everything of those terms to the right, so what is left on the left is 0. So then it becomes equal to 0. So it was a little bit tricky. I hope that you can see this pattern yourself, that this is a complete square. Yes. How you can see that this is a complete square? I can write this one in this way. Here, the first one, I can write it as x1. I write minus 1 here. Look. And then I have this one. And then I will add 1 to it. So first of all, instead of this one, x1 is x1. Minus 2 of this square root is exactly this one. Minus 1 and minus 1 will cancel. So what I have written here instead of this is completely valid because 1 and 1 will cancel and I will get the same thing back. Okay, so then the next one, and then I put them in brackets. For the next one, what I do, I write x squared minus 4. Then I would write minus 4 square root of x squared minus 4. Then I add 4 to it. Yes, 4 and minus 4 are gone. These two are left, and those are the same expressions here. And then hopefully you realize what's going on. For the next one, I can write x3 minus 9 minus 6 square root of x3 minus 9. Then I add 9 to it. 9 and minus 9 will cancel. I will get that one. And if I continue in this way, for the last one, what should I write? You know, yes? I write xn minus n squared minus 2n xn minus n squared. Then I will add n squared. N squared and minus n squared are gone, and I will get that expression. And what is left on the right is just simply 0. Yeah, it was a little bit tricky, I agree, but hopefully you have more experience now. Now I hope that you can see the pattern. Do you see that this is a quadratic pattern? Yes? How? Let me write it for you. I would write the whole expression as the square root of x minus 1, x1 minus 1, minus 1 to the 2. Yes? If I want to raise it to power 2, it becomes the first one to the 2, which gives me x1 minus 1. 2 times the first one times the second one will give me this. And the second one to the 2 is this one. So that's a complete square. It's a little bit hard to detect, might be, but then hopefully you are convinced that I am right. Let us go to the next one. Can you guess what complete square is this one? Sure you can. It becomes square root of x2 minus 4, okay, minus 4, and then minus 2 to the 2. Let us check. The first one to the 2 gives me this. 2 times the first one times the second one will give me minus 4, x2 minus 4. And the second one to the 2 will give me this one. And then the next one, yes, is x3 minus 9 minus 3 to the 2. The first one to the 2, 2 times the first one times the second one, and the second one to the 2. And finally, if you continue, the last one is xn minus 9, minus n squared minus n to the 2. The first one to the 2, 2 times the first one times the second one, and the second 1 to the 2 is equal to 0. Yes? And you know that because of this power 2, this is non-negative. This is the old trick. Now you remember, yes? These are non-negative numbers. So I have the sum of n non-negative numbers equal to 0. So it means that each one of them individually should be equal to 0, yes? So this means that this expression is equal to 0, but if this expression is equal to 0, it means that this expression is equal to 1, yes? This expression equal to 0 means this is equal to 2. This expression equal to 0, this is equal to 3, and this is equal to n. So this implies that square root of x1 is equal to 1. I raise to power 2. It becomes x1 minus 1 is 1 to the 2. But this 1 to the 2 is 1. I move it here. So x1 is 2. I got it. And the next one, square root of x2 minus 4 minus 2 is equal to 2. This is supposed to be equal to 0, so it means that this is 2. I raise it to power 2. x2 minus 4 is equal to 2 to power 2 is 4. So x squared is 8. Yes. And then, x2 is 8. And then you can continue, okay? So, for example, you have somewhere, you have xn minus n2, and then you have equal to n, and raise it to power n. Xn minus n squared becomes n squared, then you move it to the right. So xn is 2n squared, yes? So in principle, what you got here can work for everyone. So I would say that xk is equal to 2k squared. K is equal to 1, 2, 3, up to n. So these are all the numbers that I was looking for. If I put k equal to 1, 1 to the 2 times 2 gives me x1 is equal to 2. If I put k equal to 2, 2 to the 2, 4 times 2 is 8. The next one is 8, and I will continue. So I was able to find all those values with one single equation. And the reason that I could do this because it was the sum of complete squares. It was in a disguised form, but I was able to detect the pattern as the sum of complete squares and use this fact if the sum of complete squares is equal to 0, each one of them individually has to be equal to 0. Okay, so that I hope that you have learned and you have increased your knowledge about high school mathematics. Okay, I will put the link to the question paper again below this video. I really appreciate if you like the videos and you think that the videos are helpful, give me a thumb up. Thank you. By the next week. See you later.